Hey, this is Mr. Hansen. I wanted to look at something kind of cool with you today. We're working on something called shearing, and then a little bit later when we work with volume, Cavalry's principle. So the whole idea here is I've got a triangle. Let's just take a look at this first diagram. And this point on the triangle, if you think about moving this point, you'd have a different triangle, but there's something that stays the same about that triangle. So let's just do this. Let's move the point maybe right here, and then we'll redraw a triangle, kind of like this. Notice that the base of our triangle stayed the same, and the height really stayed the same too. We could draw an altitude right here that's the same as the altitude over there. So these two triangles are going to have the same base and the same height. They're obviously not congruent because their shape isn't the same. They're not going to be similar. One's not an enlargement of the other, but they have the same base and the same height. So what we've done is we've kind of transformed this triangle. It's called a shear, and with that transformation, we have preserved the area of that triangle because the base and height stayed the same. So we could find the area of the pink triangle pretty easy. It's a right triangle. We've got 3 times 1, 2, 3, 4, 5. So base times height over 2, 3 times 5 over 2 equals 7.5 units squared. And if that's the area for the pink triangle, well, guess what? The black triangle is also 7.5 units squared. And you can kind of see 7.5 squares in there maybe. You could even, there's different ways of doing this. You could break this down to say this is a 2 by 3, that's 6, half of 6 is 3 in there. And then this is a 3 by 3, that's 9, half of 9 is 4.5. And then 3 plus 4.5, sure enough, we have 7.5 units. So shearing is a nice way to kind of determine the area of a shape. You've transformed it a little bit, but you can find the area of the original shape. Let's take a look at this next one. Instead of a triangle, we have a parallelogram, and we're going to transform this parallelogram just a little bit so that we have we're going to slide this segment right here. We're going to slide it along that parallel line so it's right there. And now you can kind of see that this is going to be 6 units squared. Well, guess how much the original triangle was if that pink one's 6 units squared. Guess how much the black one is. If you said 6 units squared, you're right. It has a base of 2 and a height of 3 here. So 2 times 3 is 6. And from a parallelogram, base times height is the same thing as it is for a square, really. All you have to do is determine the height. So we can move this top part anywhere we want to, and really we could move the bottom part anywhere we want to too. So let me just make a few more triangles just to kind of prove the point here. Here's one in red. I'm sorry, I said triangles, I meant parallelograms. So this one's kind of interesting. It's very skinny and long, but it has the same area as the other two. Here's one more. Let's do this in green. Maybe right here. Something like that. That one also has the same area as all the others. So this is called shearing, and it's a really neat tool. There are some Pythagorean theorem proofs that involve shearing that are really kind of fascinating. Okay, before we leave the realm of 2 dimensions, I just wanted to take a look at this funny old shape with you here. You might notice that we have 1, 2, 3, 4, 5, 6. 6 of these figures. And if we were to break the figure down into smaller and smaller parts until it's just a line instead of a parallelogram, until it's just a line, can you see how all of those lines would be about the same length? So if we broke that down into smaller and smaller parts, you'd see lines of all the same length there. Something like that. Okay. And we know the length is a 1, 2, 3, 4. So 4 units long. And if we were to add all those pieces together, we'd have a certain height. So I broke it down into 1, 2, 3, 4, 5, 6 pieces. So 6 units high, 4 units long. And we end up at 24 units squared. So you can take shapes that are really kind of crazy, and if the cross section of those shapes is all the same length like that, if all these lines are the same, you can kind of just line them up, and rather than just have a 4x6 weird shape like that, you could have a 4x6. Let's just do this. We're just going to line them all up, straighten them out, kind of like this, kind of like that, kind of like that. You could have a 4x6 rectangle, and you would know the area of the shape. Okay, let's look at some volume. In this particular diagram, we have a cylinder, and we have 2.5 for radius, and the height is, let's just 1, 2, 3, 4, 5, 6 units high. So you might remember the formula for a cylinder. The volume of a cylinder is something like this: pi r squared. That's the base right there, and then we just times it by the height. And we have how many cubic units are in that cylinder. So pi r squared, we're going to go pi times 2.5 squared times the height is times 6. We could say times 1 height, which is 6. Yeah, times the height, which is 6. Now, I kind of want you to think about, we're going to do a little bit of extra here. We're going to say, what if we broke these pieces down into the height into sixths? We'd have a sixth is one of them, times 6. And really, you can kind of tell that this part here is just for us to understand if we were breaking this up into different size pieces, because 1/6 of 1 is just 1. But we'd get, when we do this, we get pi times 2.5 squared times 6. We get, let me try it again, pi times 2.5 squared times 6 equals 117.81. 117.81 centimeters cubed. Okay, we could also write pi times 2.5 squared times 6. We could break it up into twelfths and have 12 of them. And this piece here would still equal 1. So we can break it up into smaller and smaller and smaller pieces. It doesn't change the volume. We're just taking a look at it in terms of smaller pieces. And eventually you have like a slice of this. Instead of just a volume, you just have kind of a slice. So the best example I can give to you is maybe a deck of playing cards. And let me kind of draw a prism like this. And here's my deck of cards. Something like that. Okay. Now, if you took that deck of cards and maybe on the top it's still the same, but on the bottom maybe you slide it over a lot so it looks more like this. So it's slid over quite a bit. You're still dealing with the same slices, the same number of cards, still has the same volume. This is probably the worst picture I've ever drawn, but still has the same volume as the first deck. It's just that they're not lined up quite right on top of each other like they are in the first deck. So that's why you kind of think about breaking things down into their most basic parts, into simple slices, and then you can start to think about what we call cross sections. And if all the cross sections are congruent, meaning like in the deck of cards, if they're all the same length and width, then it doesn't matter how you spread them out. You could have a deck of cards, or you could have, which is a right prism, or you could have an obtuse prism. Let me show you an example maybe with the cylinder. If you had a cylinder that looked like that, as long as it had the same height and radius as the first one, they'd still have the same volume. So I hope this helped you start to think about cross sections with volume. By the way, this is called Cavalry's principle. If you have a shape that looks like this first one, and then you kind of take all the slices and spread it out, and they still have the same volume. And then over here we had this idea of shearing. It's really Cavalry's principle in just 2 dimensions instead of 3 dimensions. So I hope this was kind of helpful to you, and thank you and have a good day.